Hi everyone, this is Team Leo, and we are fortunate enough to provide a solution on the development of sensors for the detection of microplastics. So, what are microplastics? They are plastic particles that are less than zero point 0.5 millimeters in diameter. And why are their concentration or detection so important? If you look at some of the statistics, the global plastic production has been skyrocketed since 1950s, and it has reached to around 8.3 billion tons. Industries annually produce around 1.3 billion tons, and this figure is expected to rise even more higher to 3 billion tons towards the 2040s. And here we propose a solution that uses optical fiber-based sensor. And basically, here we change part of the cladding material of an optical fiber. For this purpose, we use a hydrogel named the polyethylene glycol diacrylate, and it has the properties of porosity. It is highly porous. It is resistant to any of its physical or chemical changes when it comes in contact with the water. Thirdly, it is optically rarer than the core material of the optical fiber. And the microplastics that are contaminated in water, they have the property to scatter any of the light wave or the EM wave. The evanescent field, which is a standing wave that propagates with the light, it gets scattered away. As we provide light at one end of the optical fiber, it passes through multiple total internal reflections inside the cable, but coming in contact with the water that are concentrated with the microplastics, they tend to scatter away the energy or the intensity of the light wave. Hence, we get a lower intensity light at the other end of the optical fiber. At the other end of the optical fiber, we use a photodiode as a detector. The photodiode converts the received intensity into the voltage signals. As the microplastic concentration increases in the cladding material, the scattering parameter also increases. As the scattering increases, the intensity also decreases. Due to the decrease in intensity, the received voltage will also be less, consequently. And as the concentration of microplastics increase, the scattering will also tend to increase, and hence the intensity that results at the other end, it will decrease, and hence the detected voltage by the photodiode, it will also decrease. So the detected voltage is inversely proportional to the microplastics concentration that enters into the cladding material. Next, we come to about the technical approach, and here we use a laser source for propagating the light energy inside the optical fiber, a photodiode for its detection, and of course a reconstructed optical fiber cable, which is nothing but the cladding material in a part of the optical fiber is changed for our daily of this purpose. And we use a ESP32 microcontroller, and since it has a Bluetooth module, we can have a real-time monitoring. The output of the photodiode is connected to the ESP32 microcontroller, and it is programmed accordingly for the real-time monitoring purpose. Here we provide a graph of the microplastic concentration versus the detected photodiode voltage. As we can see, as the microplastic concentration is less, the detected voltage at the photodiode end is even higher, and it gradually decreases as the microplastic concentration increases. Since the light gets scattered away, the received intensity is less, and hence we can conceive that the detected voltage is also less. Here we provide a block diagram that we connect a laser source with the optical fiber with the reconstructed cladding, and we have a detector at the end of the uh, optical fiber. We connect the output of the detector to a ESP32, and we can connect it to a mobile or laptop for its real-time monitoring. What is the feasibility and viability of this idea? Coming towards the feasibility, it is less complex and easily manufacturable due to the simpler parts that we use. It is having a lower maintenance cost as compared to the conventional methods. The conventional methods are like the fast Fourier transform, infrared spectroscopy, and the Raman spectroscopy. They are lab-based oriented and they take high time, are not cost effective, but it is having a low maintenance cost, the this optical fiber cable, and it is highly cost effective and portable. The previous methods, they are lab based, but this sensors which uses optical fiber cable, they are really portable and can be carried away to anywhere for their operation. It has a simpler mode of operation, so it can be handled by any person. It has a lower margin of error. Coming towards the potential challenges it poses, there might be biofouling, the growth of microorganisms on the part of the surface of the cladding material. So we propose a solution that if the regular monitoring is done, it can be eradicated. So the durability of the hydrogel is also a concern. And for its purpose, the other polymers might be considered as a cladding material after future research and developments. The initial development phase, the cost might be higher, but when mass production is done, it cost comes down to around rupees 800 rupees per sensor. Then coming towards the next impact and potential impact and benefits on the target audiences. The impacts include reduced operational cost incurred by using conventional methods. The conventional methods have a higher cost of operation, but these optical fiber sensors have a lower cost of operation as compared to the previous solutions. It provides an efficient solution for the detection of microplastics and having a less margin of error. It reduces potential harm to aquatic life, ecosystem, and human health. The water we drink, the water that is used by the industries, the water that is present in the ocean, it directly affects the aquatic life, the human health, and the industries that use it. So the aquatic life gets affected. Indirectly, the fishing industry get affected, and also the tourism industry. What are the benefits of this solution? It has a human health benefits. It reduces chemical exposure. The water we drink might contain microplastics, which damages our health, and hence their detection is important. Aquatic ecosystem benefits. It protects the aquatic life and preserves habitat. The environmental and ecological benefits. It reduces the ecosystem disruption that lives under the water. It enhances the water quality. And here we took references from some of the international journals and other sources. Thank you.